In this problem, we're given this block that is sliding along a path which is without friction until the block reaches the section of length L equals 0.75. So our block starts from here. It goes along a frictionless path until it reaches this point where we have friction with a coefficient of kinetic friction to be 0.4. So along this path we have friction. We're given that mu k is 0.4. The block passes through point A with a speed of 8 meters per second. So we're given that the speed here is 8 meters per second. If the block can reach point B where the friction ends, what is its speed there? And if it cannot, what is its greatest height above A? So in order to solve this question, we will start with the region where we have no friction, and we can say that on this region the mechanical energy is conserved, and afterwards we start studying the surface which is rough, and then the mechanical energy isn't conserved, but we can say that the change in the mechanical energy is equal to the work done by friction. So I will first label this point where the friction starts by C. And let's find the speed at C actually, in order to be able to estimate the mechanical energy at C afterwards. So between points A and C, we know that the mechanical energy is conserved. Now at A, the only kind of energy we have is the kinetic energy. Of course, we are selecting point A to be our reference level for the gravitational potential energy. At C, we have a mechanical energy which is formed by a kinetic energy plus a potential energy, because now we have a height above point A, and this height is given by 2 meters. So we can now substitute the formulas. This is going to be half mva squared equals half mvc squared plus mghc. Like we said, we want to look for the speed at C, so we can separate the kinetic energy at C and then this will give us this expression for the speed at C. And now all we have to do is substitute the values. So we know that the speed at A is 8, G is 9.8, and the height at C is 2 meters, as you must have noticed in the given. So if we solve this, this is going to give us a speed of 5 meters per second at point C. So now we have found the speed at this point here. We can now study the change in the mechanical energy between points B and C. We know that the energy that this block will have at C is going to decrease due to the friction. So the energy at C will be equal to the energy at B plus the work that we have lost due to friction, which is going to be the friction times the displacement, right? So at C, we know that the kind of energy we have is kinetic and potential. So we know that here we have Kc plus Uc. At B, we have, this is point B here. So we also have kinetic energy and potential energy. And regarding the friction, we can substitute this by mu k times n. times the distance. The distance here is L, which is given, so I will substitute D by L. Now, let's consider a few remarks here. The kinetic energy at C is easy to find. The potential energy at C is easy to find as well because we know the height is 2 meters. The kinetic energy at B is what we want. The potential energy at B, however, is not given and we need to find that. This is mgHb. If we look at the height at B, this is this whole value here, this is hb. Now to find hb, we can make use of the value of L that we have here. So we can write hb to be equal to hc plus this small extra height. So we can name this x. So hb can be written as hc, which is h actually, plus x, and h is given to be 2 meters, and for x, we know that this is going to be L sine theta. So we're doing some trigonometry here. I'm considering this triangle. We know that this side has a value L, and we know that this angle is theta because we're given that this incline makes an angle of theta with the horizontal. Sine theta will be the opposite, which is x, over the hypotenuse, which is L. So we got the height at B now. All we have to do is calculate it, and then we can substitute it in our equation in order to find the value of the potential energy at B. So we're given that theta is 30 degrees, and now we are able to find the height at B. Next, we look at the expression we have here. We don't have the normal force, and since this is a situation of an inclined plane, it's important to notice that the normal force is not equal to the weight exactly, because at any point here, the weight is vertical while the normal is perpendicular to the incline. So if we want to find the normal, we will have to project along a y-axis, and we need this angle here to project the weight along the y-axis. So if this angle is theta, then this angle will be pi over 2 minus theta, and then this angle will be theta again. So the angle that the weight makes with the y-axis is equal to theta. So the y component of the weight is w cosine theta, and then we can substitute the normal by w cosine theta. And of course, L here is equal to the value that is given, 0.75. So first I will calculate HB, so I can substitute it. So this is 0.75 times sine 30 plus 2, and this will give us 2.375, which we can round to 2.4 meters. So you can see that now I have all of the unknowns and I can solve for the kinetic energy at B. This will be the kinetic energy at C plus UC minus UB plus mu K and L. And again, we will substitute this by half mvc squared plus mg hc, which is h, minus mghb, which we said is just found, minus the value of mu k, this is minus, which is 0.4, and the normal we said this is mg cosine theta times L. So we can notice that we can simplify the mass from our equation, and we can now write VB to be equal to VC squared plus 2GH. This is H at B, so we need to distinguish that from the height at C, minus 2GHB minus 0.8 g cosine theta L. The speed at c, we found it to be 5 meters per second. Of course, there's a radical here. Times 2 times 9.8 times the height. So we look for the value of the height was 2 meters. It's given to us. So we just substitute it. Minus 2 times 9.8 times the height at B, which we found to be 2.4 meters. Minus 0.8 times 9.8 cosine 30 times 0.75 with a radical here. So if we solve this, we will be able to find the value of the speed, and this will give us an answer of 3.5 meters per second. So this is the speed at point B, which we found by studying the change in the mechanical energy, considering that the change in the mechanical energy is equal to the energy loss due to the friction.